So in this lesson, we first encountered testing series for convergence and divergence. So first of all, let's talk about what is the convergence of a series. What do I mean by that? So the sum of an infinite series is the limit of the partial sum of the finite series. So if I want to do the sum from 1 to infinity of a sub I, then what I'm actually doing is I'm doing the partial sum from 1 to n, so I'm just adding up n of these, and then letting the n, that upper limit, go to infinity. So that's really what's going on. We're never really going to have to do this. We're just going to stick with this, but this is technically what's going on. Now, if this limit exists, then the series is said to converge. If the limit does not exist, the series diverges. Now, we're already familiar with one type of infinite series, which is this one, the sum as I goes from 1 to infinity of g1 r to the I minus 1, which is a geometric series. So it converges if absolute value of r is less than 1 and diverges if absolute value of r is greater than or equal to 1. So this is one that we will need to use going forward. Okay, so here's the theorem. It says that if an infinite series is convergent, then the limit of the individual values, the terms in that series, in other words, the sequence, the limit of that sequence has to be 0. Basically, the idea here is if the numbers you're adding are not going to 0, that means you're adding a bunch of stuff. Like if that limit of the individual values was a half, that means you keep adding approximately a half and a half and a half and a half, but you're never going to settle. That sum is going to keep getting bigger. However, if these values are going to 0, it's like you're adding very, very tiny little numbers. You're essentially almost adding 0 every time. So if you're almost adding 0 every time, it's possible that that sum will settle, will stop. So if a series is convergent, automatically the limit of the individual terms is equal to 0. This is actually a way to determine if a sequence has a limit of 0. Not that that's really a convenient way to do it, but it is possible. Okay, so this brings us to our very first test to determine convergence or divergence of series. So what we do, we want to test the convergence of an infinite series. What we do is we take the individual values of the terms, we do the limit of those individual values, and if that limit is not 0, then we automatically know that the series must diverge. So either that limit is some non-zero value or that limit did not exist, then we know automatically that the series itself diverges. Okay, so here is the comparison test. It's very similar to the comparison test for integrals. So we're going to have positive sequences, so positive values of an, positive values of bn. And if we know that 0 is less than an, less than or equal to bn, for all n and z plus past a certain value, let's say k, so it doesn't have to start at the beginning. And if you know that the series of bn's converges, so if you add up all the bn terms, that converges, then automatically the series of the an terms also has to converge. Similarly, if you have the an terms are greater than the bn terms, which are greater than 0, for all n and z plus past some k, and if the series of bn terms, the series, when you add them up, diverges, then the series of an terms also diverges because that one forces that to be too big. So, very, very similar to the integral test, except now we're dealing with sequences and series instead of integrals. Another type of series that we're going to need in order to be able to do the homework for today is the p series. It's very much like the p integral. It's the series of 1 over n to the p. And it's going to converge if p is greater than 1, diverge if p is less than or equal to 1. I will justify this in the next lesson, but for today, we're just going to assume we know that the p series converges if p is greater than 1, diverges if p is less than or equal to 1. Again, very much like the p integral. So here are a few examples. So first we're going to determine the convergence of this series sigma as n goes from 1 to infinity of n squared over 5n squared plus 4. So the first thing I'm going to do is I'm going to take a look, and this is usually a very good idea to do right at the beginning, which is to take a look at the individual terms themselves. So let's consider the limit as n goes to infinity of just the n squared over 5n squared plus 4, just those terms. Forget about adding them up for a second. We're just looking at those terms. So I'm going to divide by n squared trick. This is going to be the limit as n goes to infinity of 1 over 5 plus 4 over n squared. And if I follow that limit, I get 1/5. But wait a minute, what we're saying then is as you keep adding these values up, you're adding approximately 1/5 every time. So that's going to keep getting bigger and bigger and bigger as we keep adding 1/5. So an infinite number of essentially of 1/5. So by the test for divergence, it's very important that you tell me which test you used. By the test for divergence, even though the sequence here of values had a limit, that limit was not 0, the series sigma n equals 1 to infinity of n squared over 5n squared plus 4 diverges. Okay, here is another one. The sum as n goes from 1 to infinity of 1 over 2 to the n plus 1. Now, in my head, I'm just going to see, well, what happens to those individual values. As n goes to infinity, this becomes 1 over infinity, so 0. So the test for divergence isn't going to give us any information. Just because the limit goes to 0 does not guarantee that the series, when you add all those numbers up, is convergent. So test for divergence only gives you divergence, does not tell you about convergence. So I'm going to have to sort of figure out what to do here. So I'm going to say let an equal 1 over 2 to the n plus 1. And I'm going to let bn equal 1 over 2 to the n. So I'm going to throw out the plus 1 part because that was kind of in our way. Now I want to notice as well that 2 to the n plus 1 is greater than 2 to the n for all n in z plus, which is what we're interested in. Which means that 1 over 2 to the n plus 1, 0 less than 1 over 2 to the n plus 1 is going to be less than 1 over 2 to the n for all n in z plus. Okay, so I've got a sequence of positive terms, and I know that I found another sequence of positive terms that's larger than the sequence that I'm interested in. And now I'm going to take a look at the series involving these new terms that I created. So sigma n equals 1 to infinity of 1 over 2 to the n. Well, that's just sigma n equals 1 to infinity of 1/2 to the n, a geometric series absolute r is less than 1. So sigma n equals 1 to infinity of the 1 over 2 to the n converges. And again, because of our comparison with my series, the one we were interested in, individual terms smaller than the ones that we found that converged or stuck between 0 and that value, by the comparison test, so the series we were interested in, which is sigma n equals 1 to infinity 1 over 2 to the n plus 1 converges. Now what it converges to, I do not know, but I do know that it's going to converge. So that's the comparison test on that one. Okay, here's another one. I want to find the convergence of this series, n equals 1 to infinity, sum as n equals 1 to infinity of 2n minus 1 over n cubed plus n. So first thing I would do is I would decide, are the individual values going to go to 0? And they will, because if I divide by n cubed on the top and the bottom, I end up with 2 over n squared and 1 over n cubed. That's 0 and over 1 plus 0. So I definitely will get limit of 0 of the individual terms. That's the first thing I always check. So now what I'm going to do is I'm going to let an be 2n minus 1 over n cubed plus n. And I'm going to let bn be, and I'm going to throw out sort of extraneous stuff, 2n over n cubed, which is the same as 2 over n squared. Now I want to notice that n cubed plus n is greater than n cubed, and that 2n minus 1 is less than 2n for all n in Z plus. Therefore, what we get is that 0 is less than 2n minus 1 over n cubed plus n, which is less than 2n over n cubed, which is equal to 2 over n squared, of course, for all n in Z plus. Now, this doesn't have to happen right off the bat when n equals 1, but it does, because 2 times 1 is 1, 1 minus 1, 2 minus 1 is 2 times 1 is 2, minus 1 is 1. So this numerator is positive, this denominator is positive, so this entire value, these values are all positive. Again, I could have waited until n equals 7 to make this true statement, but in this case, it's true all the time. So I've found this new sequence of bn's that is larger than my sequence of an's, and of course they're all positive, and now I look at the convergence of the series. So sigma, as n goes from 1 to infinity of bn, that's sigma n equals 1 to infinity of 2 over n squared, a p series, p equals 2 greater than 1, therefore sigma n equals 1 to infinity of bn converges. Now, by the comparison test, sigma n equals 1 to infinity of the series I'm interested in, 2n minus 1 over n cubed plus n, also converges. So that's the comparison test, and in this case, I used a p-series to work it out. So that gives you a few examples of using the comparison test and the test for divergence.